5.2 deals with the ideas of relative and absolute extrema. Here's a definition that I added to your notes. We are looking at page 4 in your note package. Extremum, meaning singular, plural extrema in calculus, means any point at which the value of a function is largest, maximum, or smallest, minimum. There are both absolute and relative or local maxima and minima. So we're talking about the extremes. What's happening at high points and low points on your graph. When we talk about relative extrema, here we are talking about local on an open interval. Relative means according to their surroundings, relative to us here in Watchus, etc. Global meaning the entirety, absolute meaning all the possibilities according to the whole graph, etc. This is on a closed interval. Relative or local extremes or maximum and minimums happen when there's a change in direction of the graph. Okay, so you can see here that that is true at points A and point B. You can see then when you draw a tangent line at point A or at point B at the change in direction, or the change in from going from a negative to a positive slope, you can see when we draw a tangent at those local maxes or minimums that the tangent line will have a slope of 0. So here we say at point A there's a local maximum or a relative maximum at, and we're looking then at the y value, and you can see I've added in the ticks on the Cartesian plane here. So we're having a local max there at point A, that is at y equals 3, and a local minimum at point B where the y value is negative 4. So you can see that when we talk about the local max or min, we're referring to the value of the function, the y. When we talk about, and we'll turn the page and look at what the x value is there. Okay, I've written this, or I've copied that same graph here. So when we talk about the maximum and the minimum points, we're looking at their coordinates. So for the max point there, the coordinates of A would be 1, 3, and the min point here would be 5, negative 4. Okay, so the point refers to the coordinates. Max and min values, that refers to the y coordinate. So we've got a max value then at 3, the y coordinate, the min at -4. The critical number refers to the x coordinate of that point. So the critical number of our maximum would be at 1. The critical number of our minimum would be at 5. So here as x is equal to 1 and 5. The slope of the tangent line, we know already from our past units, is what we call the derivative. At the local min or max point is always 0. We talked about that, and that's given by these tangent lines at the local max A and at the local max B. Both of these tangent lines at that change of direction of the graph will have a slope of 0. Therefore, these are the 2 points we will study on. Number 1, critical numbers, that's the x value, occur where the derivative equals 0. Critical numbers will occur where this derivative is going to have a slope of 0, or where the derivative does not exist. And we will look at that more in examples. Number 2, minimum and maximum points occur when the derivative equals 0 and x, the critical number, is in the domain of f of x. Let's explore those. Instead of doing the examples on 5 and 6, let's skip to the bottom of page 6 to the diagrams and the top of page 7. We'll go back to the examples, okay? Let's look at this absolute extrema, or the global extremes, the maximum or the minimum. We see we've got a couple spots where we could look at. We've got here We've got a low spot, we've got a tall spot here, a change of direction we've got here. So when we think about this, and this graph is a little bit of different than what you've got, I erased a few things. We've got a critical number here, right? We see a critical number at 0 when our slope changes here. We see the slope changing from going negative to positive here. We also see a maximum here, although the slope is not changing at that point, it just stops, it's an endpoint. And also here at the critical number -2. So we see endpoints here and here. We see some changes, a critical number here and here. And the absolute or global maximum would be here. This is the maximum. We see another critical number here, but this one is higher, right? And with the minimum, global minimum here. These are highlighted in your notes. Let's look at the next diagram. Okay, we see the endpoints here and here, although we can see that they're holes, they don't exist. And we also see right here where there'll be a change in direction of the graph. Now, it's highlighted that there's no global maximum because f of x does not exist at that high maximum point. Same with this minimum here, no global min because f of x does not exist. Okay, let's go back to the examples now. So we're asked to find the critical numbers of this function. Now I've graphed this function on Desmos and included this picture right here of this function. So you can see where there's going to be some tangent lines. Remember, the critical numbers happen at a change in the slope from positive to negative on the graph. Sorry. And so we will see a change here according to the graph, and also there's a change here, right, where the slope goes from positive to negative. So let's look up at the top. Here's the two rules that we talked about initially. Number one, critical numbers occur when the derivative equals 0, and that's going to happen here. If we have a tangent line at that curve right here, the derivative will equal 0. This has a slope of 0. Okay, that tangent line. So that's going to happen there. Right here, though, we don't take derivatives of a point. Derivatives, or that tangent line, we say it's tangent to the curve. So this point wouldn't have a tangent line. This is where the second part of this rule. Critical numbers occur where the derivative is 0, where the slope is 0, or where f of x does not exist. So we're seeing the tangent line right here at that point does not exist. So let's do the work and show what we can see on the graph. Okay, so we have the function f of x here. Let's find the derivative, which we can easily do. The derivative will be 4 subtract 4x to the power of -1/3. Okay, so the critical numbers occur when the derivative is equal to 0, or when the derivative does not exist. Okay, we've already looked at the graph, so we know the answer. The x value is where this is going to happen. Let's show the work mathematically. Okay, so if the derivative is 4 minus 4x to the power of -1/3, that equals 0. Let's solve for x here. So we subtract 4 from both sides. That's a 1. And divide by -4. X to the power of -1/3 will equal 1. -1/3 is the same thing as reciprocating it. That's a cube root. That's what the denominator and what the exponent does. And the -1 will make it reciprocate, equals to 1. What is the value of x then that makes that true? Well, x must equal 1. Okay, let's look here where the derivative does not exist. So we've got the derivative, f of x is equal to 4 minus 4. Again, I'm going to write that as the cube root of x, taking away the negative in the exponent. And now, where does this not exist? Well, we know we can't have a 0 in the denominator. And so there must be, for this function, a asymptote when x equals 0, right here. So we know here that x cannot be 0, or this happens, the derivative did not exist when x equals 0. So we've got this, or this. Oopsie, I meant just the bottom one, x equaling 0. This is where we have critical numbers. And when we look at our graph, this is true. Here we've got a critical number, the place where this graph goes from being positive to being negative, right here. We also have a critical number at x equals 1, as shown there, where the tangent or the slope of this tangent line is 0. Good. Looking at example 2 on the top of page 6, finding the critical numbers for this function f of x. Well, I did on Desmos put this function in, and we get this graph, which makes sense. It's a rational function. There are no spots, when I just look at this graph, there are no spots where this graph turns from being positive to negative, or negative to positive. So doing the work here to find these critical numbers, it should show that. I'm going to pause it and do the work and then show you. You can also try it. Remember, we're looking for the derivative. The places where the derivative is 0. Okay, so the slope of that tangent line would be 0, or give a horizontal line. Or critical numbers also happen when the derivative does not exist. So let's show that. Okay, let's look at this briefly. So here I went ahead and found the derivative. Okay, I used the quotient rule. Before we go on, let's just look at this original function. Would there be an asymptote? We can look at the graph too, right? We know that x can't equal 3 because that would make the denominator. So we see that the domain for this function is all real numbers except for x being 3. So when we look at the critical numbers now, we're looking at where the derivative will equal 0 or where the derivative does not exist. So we plug the derivative in, equaling 0, can't solve that. We cross multiply, no solution. No critical numbers from here. When we look here, where does this derivative not exist? Well, it doesn't exist when x equals 3. We can see that. However, x equaling 3 is not in the domain of this function. We talked about that up here. So no critical numbers here either. No critical numbers. We're going to do a second video for the rest of this learning of 5.2. What we're going to do here is just, you can do number 1 and 2 if you want. Check your answers in the back, or you can see I've drawn in my textbook. Don't do that on your textbook, but giving you some possible answers here. And I didn't realize I was going to share it with you when I did it, so it is very rough sketching. Number 3 is what I would like you to focus on, and also doing number 4. You don't have to do all of them, but number 3, just think through them. So what you're supposed to do is sketch a quick graph, and you should be able to remember how to graph these functions, how to graph their transformations, okay, how they shift or stretch. You're going to graph them over the interval that it's given to you. You can see whether it's closed or open. So for example, 3a, you can see here's this parabola. The basic graph would have the vertex at 0, 0. You're graphing it over the closed interval of -1, so a filled-in point there, curved up all the way to 2. And it's asking you then to not use a graphing calculator, use your own mind, examine the sketch, and see if there's any absolute or relative maximum or minimum values. I'd like you to explore this. Use the answer key in the back when you're unsure. Okay, so you can come to an understanding of what it means to be an absolute or relative max or min values. Number 4 then asks you to simply find the critical numbers. Find the values of x that are the points of change in the slope of the graphs. Remembering that critical numbers happen when the derivative is 0 or when the derivative does not exist. We did 2 examples together like this now. These you can choose to do a couple. See how it goes.